So hopefully you can see the slides.
Yes, sir.
So yeah, thank you.
Can you please?
Yeah.
Yeah. Okay, sir. Please.
Everything's fine.
Yes, sir. Yes.
Okay. Perfect. So let's start with what we. Let's start with the electromagnetic spectrum. So basically, we have the electromagnetic spectrum, which, as we know, goes from millimeter waves all the way up to waves which have a wavelength in a lot of meters. So we go from very high frequency to low frequency. So where microwave fits is basically in the range of around 800 megahertz of frequency to in excess of tens of gigahertz. So this is the EM spectrum that we are interested in synthetic aperture radar. So the radar, the history mostly is developed. The technological development happened during the Second World War. So there is a story that goes that some researchers in the US Naval Research Lab were testing whether they can communicate across a river, but they found that if there are ships between on the river, then there is a reflected backscatter. So that basically led on to a lot of questions being answered during the Second World War. And so the whole naming convention of radar, which is very weird or which is not very intuitive, is only because it was in the World War time. So nobody wanted the enemy to exactly know what frequency is being transmitted. So there are two types of radars. One is the active radar, which is the topic of interest here. And there are also passive radars. So passive radars will we will measure only the naturally emitting source of radiation. So that can be because of the sun, earth, any hot body will emit radiation. And depending on the Boltzmann constant, we can estimate what would the frequency. So sometimes the frequency range will be in the radar frequency, and that is measured using microwave radiometers. So in active radar, we have a source of our own power. And so there are a few advantage and disadvantage using radar data. So the advantage is, since we have our own source, we don't need to rely on the sun or any other radiation source. And so it's a day-night capability. Anytime we can acquire data sets. Also, radar data can penetrate. Most of the radar data can penetrate through clouds and also through inclement weather. So we have a nearly all weather capability. There are certain situations where even radar data will be affected by very heavy precipitation. So those are exceptions. The major advantage is there is penetration through the vegetation and soil structure. So because of that, we can, there are a lot many applications in the disaster mapping ecosystem domains in glaciers, cryosphere. So those are a few advantages. Major disadvantages are that there is geometric distortions and the image content is not very intuitive. So it takes a little bit of time to get used to understanding radar data. So why radar is becoming more and more popular and required is because we have a consistent global cloud cover over a lot of regions. So as we can see, this is the total cloud cover for a period of 7 years on average. And even over India, we can see that roughly 40 to 60% of the country is always covered by clouds. So during that period, optical data will not be useful. And then we always have to go for radar data. So radar basically measures the range first to a target. And so the question is, why does it always have to be side looking? Because radar is not like optical where you have the sensor pointing down and we take images. In radar, it is always side looking. So this is an illustration of why it should be side looking, is because if it was down looking, then both the points A and B on the left side will return back the signal at the same time, and we are not able to distinguish between them. Whereas if it is side looking, then we are able to distinguish between the different targets as we go along the range direction. So a simple example of how radar works is that pulses are transmitted. So if you look on the figure on the right side top, so pulses are transmitted, they interact with the object and the return is received. So if we look at the signal that we get at the receiver, is that after transmitting a high energy pulse, there is a certain time delay, which is the time taken for the radar waves to travel to the target and return back. So that is the range distance. and then we get a return from the target. So basically, because of the time delay, we can measure the range distance, and so that's how we can precisely know where exactly the target is on the ground. So what is the need for this synthetic aperture? We have this radar, but why do we need synthetic aperture radar? So it is a bit mathematical. So I've just mentioned a few equations here. No need to go into that. But basically, if let's say we want a resolution of let's say 10 or 11 meters, then the equations show that we need a radar antenna which has a length of 4,000 meters, so around 4 kilometers. So that is not possible. So what we do in synthesizing this is that for one particular target, so let's say the aircraft is moving from the left to the right of the screen. So one particular target is being imaged multiple times as the radar goes, and the total beam width of the antenna. So that antenna beam width from the start to the end will acquire n number of images every few milliseconds, let's say. So all these backscattering informations from different points on the path of the satellite, they are all combined together, and then we synthesize them. So because we are synthesizing them and then considering that the entire aperture from the first acquisition to the last for that particular target becomes one long antenna that we synthesize. So the advantage of that is that basically the azimuth resolution will just reduce to a simple formula, which will only be dependent on the length of the antenna. So for example, we have an antenna of 10 meters, then we can easily get a resolution of 5 meters. So that is where synthesizing the aperture comes into play. So an example is shown in this GIF. Hopefully it will be visible. So as we go on getting more and more information for that particular target, then on the top right side, you see that the image will become more and more clearer, because more information we have over a particular target, the better we can see it. So this is something like if you take a torch beam and if you shine it on a particular spot, and if you keep it shine, then you can look at that spot for a long time, you can see the details. But if you were to quickly scan through a dark room, then you will not be able to look at all the details in that particular area. So that is a simple analogy to what basically happens in the synthesis of the aperture. So how does this data sets look? So on the left side is an optical image of Narmada River and surrounding region. So on the bottom is the Narmada River, and then we have the surrounding regions nearby. On the right hand side is a Sentinel-1 data. I have just converted into a bitmap image, so it doesn't have that many levels of DN values. So where I'm located right now, this IIT Indore, it looks completely different in both radar and optical image, and there are some interesting things. So we can see the dam structures. So if you look at the image on the bottom, on the left hand side optical data, we are not able to clearly visualize the dams or the bridges, but on the right hand side you can see there are multiple dams on the river in this area, and we can easily visualize them. Another example which is been shown is we can see through the plumes. So on the left hand side is an optical image of this particular volcano which erupted, and on the right hand side is a coterminous image, so acquired at the same time, but here the radar data penetrates right through those clouds and we can see the ground. So this is an important application in case of active disaster mapping as well as management. So there are a few geometric distortions which need to be understood when understanding a SAR data. So one is, since we are looking in the slant range, the pixels which are near the sensor, they get compressed. So we do the range corrections when we are doing the overlaying the images on the ground. So when we are basically terrain corrections, so those will affect the SAR data. Also, there are a few geometric distortions. So they are mostly the three are there: layover, foreshortening, and shadow. And when basically happens wherever there is very high terrain, then we either get that the returns from the top of a particular mountain are coming before the bottom of the mountain, and in those cases we can see that there is a layover of the top on the bottom. Another part is there are, of course, shadows even in radar data. So, for example, if the geometry is such that we do not see the other side of a undulating terrain or a mountain, then we will just have a black backscatter from that place, and basically that will be a shadow. So whenever you think about applications, there are three major parameters in the radar datasets which need to be understood to understand which particular data or frequency will be used. So one is the frequency of radar operation, the polarization, and the incidence angle. So frequency basically will range from something like a ultra high frequency data sets, which are roughly around 800 megahertz. So P band will lie in that frequency all the way up to K band. So generally, we don't have any radars right now which acquire higher frequencies than K band because of the atmospheric parameters would affect the path of those frequencies, and so they are not particularly used in spaceborne and airborne case. So how does wavelength influence the data? So wavelength basically the penetration of the radar data through a media is highly dependent on the wavelength. So for example, the lower the frequency, the higher the wavelength, we see more penetration. So example, C band will penetrate lower through vegetation, L band will penetrate much more. So if you're looking to understand something that is under a vegetation canopy or to study the vegetation canopy, then L band and P band would be much more useful than higher frequencies. So basically this is an example of what particular like a rough estimate of how much penetration we can see. So at X band, C band, and L band. So if somebody is working with dry snow or ice and we want to see the structures which are beneath fresh snow, then L band datasets are much more useful than having X band. But if you want to see only the top layer of a soil or only the top layer of a snow without it getting affected by what is going underneath that particular layer, then X band datasets are much more useful. An example is this Landsat image in a dry region and the corresponding C band and L band data. So the geological structures which are buried underneath this dry soil or particularly a desert are much more easily visible in radar datasets. Famous example is the Nile River paleochannels. So if we look at the optical data acquired from shuttle, so we can see that the current Nile River path is clearly visible. But if you see the C-band data, then we can clearly see there is a paleochannel. And these dark regions in SAR data sets are observed wherever there is higher dielectric constant, which means there is higher soil moisture present. So basically the Nile River still has some water that flows underneath this particular patch of the desert. And then again, it meets up with the new current channel of the Nile. So these information is much easily visualized and available using SAR datasets. Through the vegetation, a similar example is shown here. So on the top side is C band, which has a higher frequency, and on the bottom side is P band, which has lower frequency. So lower frequency, higher penetration. So a higher penetration can be observed where we can see that there are these small roads which are going through the forest. So because the canopy is covering the top of the forest, so these roads are used by illegal loggers. So basically they will go through these roads with their small lorries, chop down the trees and take them off. And so they can be identified using this SAR datasets, especially at P-band frequencies. And then polarimetry. So polarimetry is basically that either we can transmit the data in a particularly polarized way. So it can transmit in horizontally polarized way where the electric field will only move in the horizontal direction, or it can be vertical. So depending on the polarization, the different structures are visualized better. For example, let's see this C-band SIRC image at L band. So we have three polarizations here: horizontal transmit, horizontal receive, that is HH. In the middle is horizontal transmit, vertical receive. So we transmit a horizontal signal and then we measure what is the signal received back in the vertical polarization. And similarly, we have VV. Now, if we combine all three polarizations, then what we can look at is we can clearly distinguish between the crop area, which is particularly dominated by the HH and VV polarizations, and the forest region or covered canopy regions, which are mostly dominated by the cross polarization or HV. So distinguishing between different land cover types is a major application using polarimetric SAR datasets. So why this happens is because there are we distinguish into the SAR backscatter into some basic scattering mechanism. So we say that whenever there is a rough surface, the backscattering will happen, and we will get a single bound scattering. Wherever there are regions which will form a L-shaped, let's say, target. So particularly this is formed in the urban regions where we have scattering coming from the road, and then the wave bounces from let's say part of the building and then goes back to the sensor. That is something we characterize as double bound scattering. And there are complicated scatterings which happen from the vegetation typically. So those are volume scattering. So even if we consider these three very broad scattering mechanisms, then we can visualize them and we can use them to distinguish between different land covers. So this is an example of the San Francisco Bay, where we have a few land cover types of interest. And if we combine the three scattering mechanisms from a polarimetric SAR data, then on the right hand side, we can see that combined image where we have this HH plus VV backscatter as blue, and then HV as green, and HH minus VV backscatter as red. On the left hand side is a Google Earth image. So we can clearly see that the ocean, which mostly will be having a rough surface or a smooth surface in cases of very still water, that will basically give us surface scattering, which is shown here in blue. Most of the vegetated regions will give the backscatter in the cross-polarized channel, which is green, and the urban areas which will have this dihedral scattering. So basically L-shaped structures where there is a road and there is a building. So those will have this distinct double bound scattering, which is red. So urban regions will have a combination of dihedral scattering from the corners. They will also have surface scattering coming from top of the roof and also from the roads, and also they will have some cross polar scattering or the or volume scattering, which are coming from all the vegetation which are there near the roads, so on the boundary of the roads. So these combined, we can easily distinguish between the different land cover classes in this using this particular method. So another important thing is to look at the dielectric constant. So more dielectric constant means there is more water content. More water content generally means that the backscatter will be much more darker, because water content will smooth out that surface and most of the backscattering will be away from the sensor. So this is used a lot in geology applications for SAR data. So here we can distinguish between mud and limestone. So mud will have much more water content, so the SAR backscatter is darker because most of the scattering is going away from the sensor. And then limestone is much more drier. It will reflect most of the backscatter towards the sensor, so it is brighter. So this can be easily used in lithological mapping, geology, and its applications. Agriculture applications, there are a wide variety of applications going into agriculture. So a simple example is to distinguish irrigated fields. So these are typically these circular fields which have a central feeder and hopper, and those will be irrigated, and the surrounding regions would not have the same soil moisture or the vegetation water content. So these can be easily distinguished, and we can measure exactly how much soil moisture and vegetation moisture is there in SAR data. So those are some applications in agriculture. So now coming to data access. So right now we have only the Sentinel-1 platform. It's a C-band sensor provided by the European Space Agency, and it's been continuously acquiring data since 2014 to present. So this is an open free data sets which is available from these two particular links. One is the Alaska Space Facility Data Access Center, and the other is the Copernicus platform data access, which is provided by the European Union. So that data is acquired every 12 days at present over India. Over Europe, it is acquired every 6 days. There is another sensor which was active in the past. It is called the ALOS pulsar. It is at L band, but it was only active for 5 years. So that data is now available on, again, ASF. And then there is the UAVSAR data. So this is an airborne data acquired over certain area of interest that the funding agency NASA JPL has, and it acquires in different frequencies, L band, C band, and P band. And you can use those acquisitions over Greenland, Africa, and over different sites in mostly in the United States. So if we quickly go over to so this is the portal for searching for Sentinel-1 data on the ASF vertex. So you can basically go to any particular region of your interest and you can draw a rectangle, and then you can provide some parameters like what would be the start and end date. And if you don't provide, then it will just take all the data set that is available from the first acquisition to the current. And you can see these data sets here. So these are all provided freely. You can use them. You can use repeat pass data sets to do any time series analysis. Here is a look at what the data will look like from the two polarizations. So again, here we can see the Sardar Sarovar Dam is we can see in this particular piece. So this data, using a simple login you can create, you can download these data sets. So going back to okay, so going back to the data access. So this is currently the available data sets. So in near future, in a couple of years, NASA and ISRO will be launching the NISAR mission. So it will have L band and S band sensors. And the good thing is that the data is completely free. It will acquire every 12 days in L band, and that has huge applications, right from ecosystems to cryosphere to disaster mapping. So the best tool right now for processing SAR data for beginners is to use the Sentinel applications platform, Snap. So this can be useful to process the Sentinel data as well as ALOS pulsar data that is available currently. So a general example of the data processing workflow, the post-processing. So we use the level 1.1 single look complex data sets, and then we go through this whole process. So it is being already published in a lot of reports, and also there is an MDPI paper about it. So I have mentioned the link here. So basically we go through, basically download these Sentinel data sets, and then we apply the orbit files. So these orbit files will provide you a precise orbit location, and that helps in accurate geolocation of the data. We remove the thermal noise, apply radiometric calibration. So all these steps are basically just single click functions in this Snap toolbox. And they basically would help you go through the entire processing workflow. You can even customize this, and you can make a processing workflow in such a way that it can process multiple data sets at once, and you don't have to do it manually every time. So finally, coming to look at a few applications of what SAR data can do. So some basic applications are in ship detection. So ships have a different kind of characteristics than the surrounding water. So due to the metallic nature of the shipbuilding, it has a very high reflectivity. And so we can use that reflectivity to identify the ships. Another question is, can we identify the direction of the ships? So that direction can be measured from something called as the wake. So the radar, it also detects, it also is sensitive to the displacement during the motion of the radar. So basically what that does is that because the ship is moving either towards or away from the radar, the wake that is created, that is the water breaks when the ship moves. So that has a slightly different signature than the surrounding water. So there is a displacement between the actual location of the ship and this particular wake, because the wake is stationary, but the ship is moving. And based on that particular displacement, we can estimate the velocity of the ship and also estimate the direction of the ship. Another application is oil spill detection. So when I was doing my postdoc, we had oil spill near JPL Caltech, and it was on the Huntington beach in October of 2021, and we captured this particular Sentinel-1 data SAR backscatter. So these darker patterns in the ocean that we see, these are all the oil spills which are coming from this particular port, and then we can estimate where this oil spill will go and how to mitigate this oil spill further. In forestry, there is a lot of applications. So there is actively research is going on in estimating the carbon content of the forest, how much it is lost during deforestation. Another important application is to distinguish between plantations and natural forest. So using dual pole data sets, we can, and time series, we can do that. So for example, here on the right hand side, the oil palms are easily distinguished from acacia plantations. So oil palms have a canopy. So it basically is a palm tree like coconut, and then because of the particular structure of the tree, we see a lot more penetration of the C band through the ground. So we see a lot of dihedral scattering is coming. While acacia plantations, they have a lot more closer plantations. So we see a lot of volume scattering coming from this. So this time series SAR data can be used for distinguishing plantations from natural forests. Another example is to do land cover classification. So this is an example using JERS L-band data. And on the left-hand side is optical, right-hand side is left-hand side is a SAR backscatter, and right-hand side is a land cover classification data sets. Rice mapping is another which is being done operationally. So there are a lot of agencies which produce these maps for the rice. And so the major distinguishing factor is, if you look at the left-hand side, we see a lot of this magenta color. So this magenta color is coming because of the horizontal backscatter is dominant. Why that happens is this rice have stalks, and underneath there is always this flooded water in the initial stage. So because of the stalks are vertical, the vertical wavelength will have a lower backscatter, while the horizontal wavelength is interacting with these stalks in the underlying water much more. So because of this, we get this typical dihedral scattering from rice. And so if we look at these backscatter profiles in a time series, then when during the plantation period of the rice, this is dominant. And so using that, it can be easily estimated how much area or acreage is being the rice is being sown into. And so that is operationally useful to estimate how much will be the production of rice in that particular area. So SAR data is used in that. Another part is to do forest height and structure mapping. So this is something that we do for using the UAV SAR data. We also do using Dynamics data sets in the past. So what basically we want to do is we want to estimate the vertical structure of a forest. And then we see this 3D nice tomograms. So the figure in the middle, what you see is basically how the forest scattering is behaving in a 3-dimension. So on the vertical axis is the elevation, and on the horizontal axis is the range distance. So we can map out all the different vertically oriented scatterers, how the forest is looking at in the vertical profile. And that is useful to estimate the growth of the forest, to estimate the carbon content in the forest, as well as to estimate what is the understory of a particular forest. So SAR data, since it penetrates through the vegetation and is sensitive to dielectric changes, it can be used to measure the sub-canopy flooding. So sub-canopy flooding is something that is very common in peat forests, especially in the let's say in the Sundarbans or in Malaysia and Indonesia. And these are not easily visible using optical data because the canopy blocks. But you can see that on the figures below, the P-band image is acquired in the dry and wet season. And in the wet season, we see a lot of heavy backscattering that is happening because the waves are interacting with the water, which repel, and then interacting with the trunks. And because of this dihedral scattering, there is a huge backscatter that is coming towards the sensor. So that is basically providing us with very high backscatter, and we can easily distinguish the sub-canopy flood mapping. Again, in geology and paleochannel mappings, as we saw with the Nile, this is very useful SAR data because it penetrates through this dry soils, and it can be easily used to map these paleochannels. Another important application is to do SAR interferometry for disaster mapping, subsidence mapping. And so that basically provides us with an information of how much a particular region is subsiding over a period of time. So for example, this is a subsidence map of Berlin, and we can see there are regions which are subsiding at the rate of 6 millimeters per year. So this is important to monitor critical infrastructure. If there are buildings and apartment housings in that particular region, then they need to be reinforced. So SAR data is useful in those cases. Also, earthquake deformation mapping is done, and we are here seeing an example of the BAM earthquake in Iran in 2003. And so this was a huge earthquake, and using SAR interferometry, we can map out exactly what was the epicenter of the earthquake and how much is the deformation that is happening. So using this fringe informations, we can then decode the estimate the deformation, the extent of disaster that would happen, and then analyze those impacts. Similarly, vertical motion tracking is done. So Mount Etna is an example of an active volcano in Italy, and we can see here that it is deforming vertically, and there are deformations of the tune of plus or minus 15 millimeters per year. Basically means that some of the regions are having a deformation in the negative direction, that is depressing, and then some regions of this volcano are coming up. So basically these are then used by volcanologists to understand whether when and how this volcano might erupt, and to do mitigation studies. So a few takeaways are that we see that synthetic aperture radar, this is an active remote sensing technique. It has a lot of applications because of its all-weather capability, penetration through the ground. The major things to focus are to always look at the frequency of acquisition of SAR data, the polarization and incidence angles, and those would have a lot of impact on how well we can estimate the structure of a particular target, the changes, the dielectric constant, and the roughness. So so this has been a very quick lecture, and I've tried to give a gist of the basics as well as go into providing you with information on what will be the typical applications of the data sets. And I've intentionally kept some time for questions because this is not something which is very focused towards one application or focused only on the pre-processing and post-processing part of the SAR data. So I'll stop here, and I'll be happy to answer any questions you have.